All right, folks. Today is an important day. So we've been, last class, we looked at, can we extend our definition of what an angle means to include angles that were of any size, right?
Yes.
We did that via this standard position angle thing that we did, right? Today we're gonna now connect that to sine, cosine, and tangent. So it's a big connector day, okay? So just kind of, we'll get to the payoff here, but we have some hoops to jump through first. Again, I want to warn you guys that I'm gonna be like constructing something along the way. Will you be responsible for like duplicating the construction? No. What will you be responsible for? Being able to use the result, right? Just like when we came up with what a radian is, what you really need to be able to do is convert from degrees to radians or use that arc length formula. You don't have to repeat the construction of what a radian is or how to find the conversion factor. Same idea to the start here, okay? So what I want to do is I want to start by drawing the standard position angle for a 30, 150, 210, and 330 degree angles. So I'm going to color code these so we can see them all on the same axis. So a 30, and we'll do like 210. And then we'll do, which looks good. And then that's a 330. So if we inspect this visually, what do you kind of notice here? Yeah, Josiah.
The 180, no, the 150 and the 330 are on the same, but they're like the same.
Yeah, they're kind of the same, right? As are the 30 and the 210, right? They're supposed to be. Matt?
So the 150 and 330, and then the 30 and 210, respectively, they go in straight lines. So it's not like a lopsided. I think they're pretty much like a straight line after we take both of them.
Yeah, yeah. So this is an important observation, right? So what is, if they are going, if, you know, the blue and orange and the green and red are both on the same straight line, what is that going to say about those angles? Josiah?
They're equivalent. They're inverse.
They're all the same,
Yeah.
right? Those are all the same angle measures, right? Under this 30-degree angle, well, obviously that's 30 degrees, right? If I look at the 150, I did 90, 60, and then what's left down here? Underneath the terminal side here, between the x-axis. 30 degrees, right? Because we did 90, 60, 30 more makes 180. How about between the x-axis and the green angle? 30. Also 30. And how about the x-axis and the orange angle? 30. 30. So the important observation here to make is that these terminal sides of these four different angles are all just like a reflection of each other, right? Whether we're reflecting across the x-axis or the y-axis or the line y equals x. These are just like a reflection from geometry. You guys remember this term from geometry? Do you remember what property reflections have? They're going to maintain congruency, right? That those two figures are going to be congruent across a reflection. Nothing, the size and the shape of them didn't change, just the orientation, right? Is everybody okay with this notion? Great. So that's the important piece. So we're going to define these angles here that we've written in as a reference angle. A reference angle is the angle formed between the terminal side of a standard position angle and the x-axis. Okay? So each one of these 30-degree angles are a reference angle. The reference angle for the 30 degrees is the 30. The reference angle for the 150 is the 30. The reference angle for the 210 is the 30. The reference angle for the 330 is also 30. Is everybody okay? All right. Now suppose we want to take this 30-degree angle that we started with, the red one, and turn this into a right triangle that also contains that 30-degree angle. So I'm just going to pick a point on that terminal side. I'm going to call that point xy. And I'm just going to drop a perpendicular down to the x-axis. So now I have a right triangle that contains that 30-degree angle. Everybody's good? And you know what? For the sake of clarity for you guys, I'm going to instead call this point, instead of x comma y, I'm going to call it a comma b. It's a little abusive if I keep calling everything x, y. I'll call it a comma b. Is that okay? Okay. Everybody's okay with what we did there, right? All right. Can we do the same thing to make a congruent triangle using the other reference angles? Sure, right? What point will I end up picking here on the blue one? What will the name of this point be? Negative a comma b. Very good. Why is it negative a?
Because in the second quadrant.
Yeah, we're on the left of the y-axis, right? When we move left on the x-axis, we get negative values. Good. So we can do the same thing there. If we take the green angle, I'll make that longer, and we do the same thing, what will be the name of the point here? Negative a comma negative b. Okay. And we do the same thing on the orange guy. What are we going to have here? Yeah, a negative b. Very good. Everybody agree? What can we say about these four triangles? They have to be congruent, right? Because I know for this triangle, what is the height of this triangle have to be? The red triangle we're looking at, what does the height of that red triangle have to be? Have to be b, right? Because to plot a point, we go like a over and then b up. Agreed? What will the base of this red triangle be? A. Does everybody feel okay? And I can make the same argument for the blue, the green, and the orange triangle, right? So for sure they are congruent. They have the same angle measures. They have the same side lengths. We know they are congruent. If they're congruent, what can we say about the values of sine, cosine, and tangent? They have to be the same, right? The values of sine, cosine, and tangent in the red triangle will be the same in the blue triangle, and the green triangle, and so on and so forth. Everybody good? Okay. So let's look at this red triangle. Let's focus here for a moment. So we have side A, side B, what's the hypotenuse gonna be?
A squared plus B squared.
And then square rooted,
Yes.
right? So I'm gonna give that a name, I'm gonna call that R.
Why R, just out of curiosity?
It's the kind of the traditional name for the hypotenuse. In this context, we're gonna call it R. You'll see why when we get to the end, why I chose the letter R, because this actually gets another layer built on top of it.
Okay, got it.
But for right now, we're just gonna say, that's the traditional name we give to it. We just picked a name, we picked R. You'll see it makes sense in a moment. Well, maybe next time, depending on how much time we end up having left. Everybody's okay still, right? Okay. So, for example, so we're good here, right? We did that. So these triangles that we drew, these have a name. We call these reference triangles. So that's a triangle formed by drawing a line from the terminal side of a standard position angle that's perpendicular to the x-axis. Okay? Everybody feel good? Okay. So we already noticed that geometrically these triangles are identical, right? They're congruent. They have all the same measures. They have all the same side lengths. The angles are the same. The only difference in them is their orientation. But what about algebraically? How are they different? What's different about these triangles? Let's move back up to look at this. Because there's an algebraic difference. Max, do you see?
They have different points.
Yeah, exactly right. So the point on the terminal side to make the triangle is different, right? The coordinates are different.
So because it's on a graph, if we were calculating the side, we always say we can't have negative sides. But in this case, we would be able to say that the side is actually negative.
So what we're going to do in just a moment is we're going to, instead of talk about the side of the triangle, we're going to take this and talk about the point on the terminal side. And because we're going to talk about a point rather than a side of a triangle, the coordinates of a point can be positive or negative or zero, where the side lengths of a triangle certainly can't be negative or zero, right? Everybody's okay? So if I look at this red triangle, we can say that, sine of theta is opposite over hypotenuse, right? So in this triangle, that is like A over R. I'm sorry. Well, I guess sine, be careful. So sine 30 is going to equal B over R, right? Everybody's okay? And now remember that B, in addition to being the opposite side, is also the y coordinate from this point on the terminal side of my standard position angle. And R is the hypotenuse, but it's also the distance from that point on the terminal side to the origin. This is how we're going to now connect opposite adjacent hypotenuse to these standard position angles that are bigger than 90 degrees, right? We can't draw a right triangle to do this. What we can do is we draw these reference triangles that are equivalent to the first quadrant, or triangle in the first quadrant, and instead of using opposite adjacent hypotenuse, that's the same thing as using x, y, or r. So that's where we fall off at here. Put this all together, and we have this definition here, or set of definitions here. Is that for a standard position angle theta with point on the terminal side of that standard position angle with coordinate x, y, and a r equal to the distance from that point x, y to the origin, aka the square root of x squared plus y squared, we can say that sine theta is y over r, cosine theta is x over r, etc., etc. Josiah.
I assume for the cosecant, secant, and cotangent, it's saying that applies when x does not equal 0.
Well, when the denominator of the fraction is not 0, right?
Because you can't divide by 0.
Right. Why don't I have to worry about it over here with the r's?
Because you're not dividing by
R is a distance between a point and the origin. The origin is not technically a point on the terminal side, right? It's the vertex, so like you can't ever have R to be 0, so those ones are clean. We don't have to worry about it there. So the takeaway here, oops, the way to remember this is that y just means opposite. X just means adjacent. Hypotenuse just means r. And now this is the exact same thing as SOHCAHTOA, right? We're okay? So again, this is the piece that we're going to be using to do problems, and we'll do some examples here in a second. I'll give you a chance to practice with some classwork here in just a moment, okay? I just need to want to let this sit for a moment, let you digest what we just did. So again, the idea here, we started out, we're sine, cosine, tangent of theta. We're tied to acute angle, or limited to acute angles in a right triangle. We said, okay, well, we need to be able to draw angles that are of any size. We created the standard position way of drawing it. We took that standard position way of drawing our triangle and made some clever observations and found that, hey, if I pick a point on the terminal side of my standard position angle, the x coordinate acts the same thing as adjacent. The y coordinate acts the same way as opposite. And the distance between that point and the origin is just like the hypotenuse. And now I can take SOHCAHTOA and replace side lengths in a right triangle with coordinates on the terminal side of a standard position angle. This is our standard position, point on a standard position, or point on the terminal side of a standard position angle definition. We have one more phase to get through before we get to the final form. It's like one of those video game bosses where you beat it once and you think, I'm done, and then it changes and like the armor falls off and it's worse than before, and it's like, okay, I'll beat this one, and then he beat that one, and then like something comes out from behind. It's like, no, I was really the bad guy the whole time. It's like, oh, is this final boss ever gonna end? It's kind of like, there's just 3 forms, guys, don't worry. It does have an ending. Okay, I'm gonna pause here. Okay, so I have this one. Oh, we did that already. No, this one's the one I want. So we're gonna pause here and do a Delta Math classwork assignment. I want to preview how to do these problems before we dive in. Okay. So here the directions say to find an angle coterminal to -906, where that angle is between 0 and 360. How do we find coterminal angles?
What is coterminal mean? Is that like a negative point?
No,
Is it
like
finding a
where
terminal
would
point?
would be if you like go around like a new one, you go around another one, just like 30 degrees, but then if you go around another cycle, it is 390.
So coterminal means that you have two angles whose terminal sides occupy the exact same location. So Max's example was like 30 and then 390 both occupy the exact same location, because the only difference between 30 and 390 is 390 you go around one full time and then you do 30 degrees. which puts you in the same position as 30. So the shortcut in terms of finding coterminal angles, you're just going to be adding or subtracting 360. So what am I going to do with this problem? I'm just going to keep adding 360 to negative 906 until I get an answer between 0 and 360. And then I type in my answer and press enter and I'm done. Okay? So you can add 360 or subtract 360 as many times as you need. Is everybody okay? So the next idea here is we're going to take our angle measured in degrees and decide what quadrant it lies in. Okay? So look at the example here. So 225. So my quadrant 0 to 90, 90 to 180, 180 to 270, 270 to 360. Or quadrant 3, right? Because we're between 180 and 270. Oh, I didn't see that it changed. Anyway, you're supposed to complete 10 of them inside of 100 seconds. You'll see that, like, once you get the hang of it, it's, you just have to decide, like, which quadrant is it in between. And if it helps, draw yourself a picture with the quadrants 0 to 90, 90 to 180, 180 to 270, 270 to 360. Should be okay. Ooh. This is not what I thought I was going to give you. Huh, okay. I thought I picked a different problem for this. Okay. We got to talk a little bit more. All right, before we can do that, I lied. We're going to talk a little bit more first, and then we'll do this classwork assignment. My apologies. Everybody okay? So just put a pin in this. We'll circle back to it. But before we can do that last problem, I want to talk a little bit more about what's going on here. Okay? All right. So we've tied sine, cosine, tangent, secant, cosecant, secant, cotangent to coordinates on the terminal side, right? So if I go back and I think about this, I have my 4 quadrants. Okay. In the first quadrant, x is positive and y is positive. Everybody agree? In the second quadrant, x is negative, but y is positive. In the third quadrant, both x and y are negative. And in the fourth quadrant, x is positive, but y is negative. So if I go and I look here at my sine, cosine, and tangent, in the first quadrant, sine is positive or negative? Right? Positive, because y is positive in the first quadrant, and r is a distance, so it will always be positive. So sine would be positive in the first quadrant. How about cosine? Also positive. What about tangent? Okay. So what I'm going to write here is A for all in that first quadrant. That's going to help remind myself that in the first quadrant, all of my trig functions, sine, cosine, tangent, and reciprocals are positive.
I have a question.
Yes.
How can we just so we're saying because because sine is equal to a side over a side, the fraction that results that will be positive or negative. Because at first my question was like, if we're measuring angles, why would it matter what quadrant it's in if an angle is an angle?
But this is a ratio of side lengths.
There's a ratio of side lengths.
But not really anymore. Now it's a ratio of coordinates.
Okay, so
from
if
the
we're doing a
terminal
regular
side.
triangle with no graph, we would just still keep it as whatever sides, all the sides are positive. Here we're saying that because the side can have negative points.
Because we're no longer talking about sides. We're talking about coordinates from a point on the terminal side of an angle. And because we're talking about a coordinate now, not sides, coordinates can be positive or negative or zero.
Oh, okay.
So that's what we're saying.
So if we have a triangle like this, right, and up here it's, 1, 0.
There's no more triangle. There's no more triangle. There's just the point. That's all we have. That's all we need. Right? So like, right? So R is gonna be 5. Negative 4 squared is 16. Negative 3 squared is 9. 16 plus 9 is 24. No triangle. So this is my angle theta. So sine theta is just gonna be y over r. No triangle drawn, just using the point. Now we got the formula y over r by building these triangles out. That's like the source. But what we did was we translated the triangle into a point. The triangle definition turned into this point definition.
Okay, that makes more sense.
That's what we've done. Is that
Yes.
good? Okay. All right. Let's look in quadrant 2. Okay. In quadrant 2, sine, positive or negative? Positive, right? Because the y coordinate's positive, r is always positive. Cosine, negative. Tangent, negative. So here we have, I'm going to put an S here for sine is positive, and obviously, and it's reciprocal, right? Is okay? So in the first quadrant, I wrote A for all your trig functions are positive. In the second quadrant, sine and its reciprocal are the only ones that are positive. Let's look in quadrant 3 now. Sine, positive or negative? Well,
Negative.
the y coordinate's negative and r is always positive, right? So that's a negative. Cosine,
Positive. No, negative.
negative. X is negative and r is always positive, so that's negative over positive, that's negative. Tangent, positive, because that's a negative over a negative. So I'm going to put a T here for tangent positive, well, and it's reciprocal, right? Cotangent counts too.
Like, I don't understand how you figure out that it's positive or negative. Like,
So, for example, we looked in the third quadrant. Sine is y over r. Anything in the third quadrant is going to have a negative y value. And the r is a distance, so that's always positive. If I have a fraction that's negative over positive,
if the
that's going to
answer
give you a
would be-
negative
I
number.
see. Okay, so the, like, we're saying what the answer would be?
Yes.
Okay, thank you.
Is that
Yes.
fourth quadrant? Same thing. Sine is going to be positive or negative. Oop. Negative, right? Because the y value is negative and the r is positive, so negative over positive is negative. Cosine, positive, because the x coordinate's positive and r is always positive. Tangent, negative. Y is negative, but x is positive. So here I'm going to write a C, which means cosine is positive and it's reciprocal. So the mnemonic device that I remembered, or what I was taught when I took this course a long time ago, to remember ASTC, we remembered all silly turtles crawl. I don't know why. I think just the teacher came up with 4 words that kind of make a sentence, but that's the way I remembered which letter goes in which place. And again, what A means is that all your trig functions are positive. S means sine is positive and it's reciprocal. T means tangent is positive and it's reciprocal. And C means cosine is positive and it's reciprocal. Okay? With what we did here? So again, this is the shortcut, right? So now if I go back to this delta math problem, it says which quadrant is cosine positive and tangent positive? So if I go back and I look at my piece, here sine is positive and it's reciprocal. That ain't it, right? Here tangent's positive and it's reciprocal. That isn't it because cosine's negative there. Here cosine's positive and it's reciprocal, but it's not going to be it because tangent is negative. Quadrant 1, where both of them are positive, everything is positive, is the only one that can work. So I'm going to pick quadrant 1. Okay. Here, the next one says secant's positive, but tangent is negative. Remember that secant is the reciprocal of which trig function? Cosine. So I want the place where cosine is positive and tangent is negative. If I look at my picture, cosine is positive. These are the two choices. But tangent is positive here. It's negative down here. We want quadrant 4. Right? So am I doing any calculation here? Just looking at this kind of table that I built for myself and using that to be like, okay, where does this fit? And that's all. That's all I need to do. You guys feel okay? Okay. Yes, go ahead.
How can tan and cotangent be? Why wouldn't it be all negative in the third quadrant?
Because y over x is negative over negative,
Oh,
which makes it positive.
I'm an idiot, sorry.
That's okay. All right, I'm gonna pause here. So let 5 comma negative 12 be a point on the terminal side of a standard position angle. And I guess we'll call this standard position angle theta. Find the 6 trig ratios. So, because we're talking about a point on the terminal side of a standard position angle, we're going to be using those new definitions, right? Y over R, X over R, etc. So the first thing I'm going to do is find R. Five squared is 25. 12 squared is 144. You add those together, you get 169. The square root of that is 13. Is everybody okay with how I found R? Okay. So, according to my new definition, sine is y over R. So that's going to be negative 12 over 13. Done. Cosine is x over r. So that's going to be 5 over 13. Tangent is y over x. It's going to be negative 12 over 5. Cosecant is the reciprocal of sine. Secant is the reciprocal of cosine. Tangent is the, cotangent is the reciprocal of tangent. Right? Is this any more difficult than if I give you a right triangle with two sides and ask you to report the 6 ratios? No. We're just using different formulas, right? But it's equivalent because the only difference between these formulas is I've replaced opposite with y, adjacent with x, hypotenuse with r. That's it. Have we really done anything different? We just kind of changed the names of some stuff. But like everything works exactly the same, which is wonderful. When like our new definition just like takes the old definition and extends it out. That's all we've done. Is everybody okay? Okay, we have one more final phase because we have one little tweak we can do to this to make this even a little bit easier to deal with. And I want to preview that while we have 2 minutes. I'm not going to write anything down, I'm just going to talk. Okay? What's the one thing that we're choosing when we do this? It's where we're going to choose that point on the terminal side. Right? We have infinitely many choices of where to pick that point on the terminal side. We're going to standardize this process by saying the point we're going to pick is always going to be, we're always going to have this property. And then what happens to these formulas after we do that? And that'll be our final form of this. And we'll handle that next time. But that's it for today. Everybody's okay? This one okay? Yeah? I hope so. I tried really hard to find a way to present this that was gonna like intuitively, all this stuff was gonna fit in together without having to like over symbol it. We just kind of drew some pictures and looked at congruent figures and built this geometrically rather than algebraically, which I think we're probably more comfortable visually looking than like sorting through a whole mess of symbols and like what does this symbol mean, what does that symbol mean, like what are we talking about again? We're just looking at the triangles and the pictures and the angles and it's like, okay, yeah, I see what you're saying. Of course, that has to be how that would work. That's what I tried to go for here today, to make it so you get the intuition without having to like have so much algebra. Anyway, good, thank you.